Look at this fuel car's wheel rim. Hollow, deep, and full of mechanical beauty. This is what industrial design should look like in our minds. But turn around and look at today's electric vehicles. Why are the wheel rims so ugly? They don't even have a single cooling hole. Aren't EV owners afraid of their brakes overheating on downhills, causing brakes to fade? If you think this is just to save money, then you are vastly underestimating this round disc. Today, we are not just talking about wheel rims. We are going to thoroughly dismantle the physical limits behind the EV chassis, taking you through the chassis trilogy, extreme tires, fully enclosed wheel rims, and the cursed unsprung mass. This is not automakers trying to rip you off, but rather to fight against that 2-ton physical limit. A crazy trade-off engineers were forced to make. To understand why this disc looks so counterintuitive, we must first start with the most basic physical properties of EVs, which is the precise calculation of energy recovery and thermodynamics. In the era of traditional fuel vehicles, we only had two requirements for wheel rims. First is strength, and second is heat dissipation. Because when a fuel car decelerates, it relies 100% on mechanical braking, which means using brake pads to desperately bite the disc, converting all the kinetic energy of those 2 tons into heat and releasing it. On long downhills or during aggressive driving, the disc temperature can easily break through 300 to 400 degrees. At this time, the large holes on the rim act as life-saving fans. Without these hollow designs to draw in cold air, the brakes would quickly fade due to overheating. This is also why racing rims are designed to be as hollow as possible. But electric vehicles completely overturn this logic. EVs have a powerful kinetic energy recovery system. In the vast majority of driving scenarios, the reverse drag generated by the motor is enough to handle over 90% of deceleration needs. This 90% of kinetic energy doesn't dissipate as heat, but is converted into electricity and stored back in the battery. This means the tasks that actually heat up the disc account for less than 10%. According to engineering data, the total thermal energy generated by an EV's braking system is reduced by over 80% compared to traditional fuel cars, since powerful ventilation and heat dissipation are not needed. Engineers turn their attention to another, more core enemy, and that is aerodynamic drag. In fluid mechanics, about 30% of the air resistance a vehicle encounters while driving. The area is generated by the tire and wheel rim. When a hollow rim rotates at high speeds, it's like an out-of-control air blender. It stirs up the smooth airflow passing by the side of the car into a chaotic turbulence and sucks it into the wheel arch. This chaotic airflow generates immense resistance, like an invisible hand desperately pulling the car back. And this flat, round wheel cover that everyone finds ugly was born precisely to resolve this 30% drag. The fully enclosed design allows the air to glide smoothly over the tire surface like cutting through butter, preventing it from entering the inside of the rim to cause trouble. Experiments prove that this low drag design can help EVs regain 3% to 5% of range during high-speed driving. You might think 5% doesn't sound like much, but today, as battery technology hits a ceiling, engineers wanting to increase range by 1% might have to burn hundreds of millions of dollars. Now, just by changing the rim shape, they get 5% for free. For engineers, this is simply the most cost-effective deal in the world. This brings us to the second chapter of our trilogy, the cursed unsprung mass and weight balance. Although enclosed rims are excellent for aerodynamics, if, for the sake of sealing it, the entire alloy wheel is made into a thick solid disc, that weight would be a disaster for the shock absorbers. In chassis engineering, the weight below the shock absorber spring is called unsprung mass. The laws of physics tell us losing 1 kilogram of unsprung mass equals losing 10 kilograms of sprung mass. If the wheel rim is too heavy, the shock absorbers, when handling potholes, will react slowly due to excessive inertia, resulting in the whole car feeling stiff and constantly vibrating over bumps. The perceived comfort level drops directly by 20%. This is why many EVs comes from the factory with a smart combo of lightweight alloy wheels and low-drag plastic covers. The inner alloy wheel is made into a slender spoke-like shape to pursue extreme lightweighting. A flat, thin plastic cover is then placed on the outer layer to handle the aerodynamics. This design is not only 15% lighter than a fully enclosed aluminum alloy disc, but also allows you to spend just a few $100 replacing the plastic cover if scratched, rather than tens of thousands on a whole new alloy wheel. Next, we must turn our perspective to the heaviest part of the trilogy. Electric vehicles are 400 to 500 kilograms heavier than fuel cars of the same class. This massive deadweight is a physical massacre for tires. When you make an emergency lane change at high speed, the lateral stress generated by this 2-ton behemoth will instantly collapse the sidewall of a regular fuel car tire, so EV tires must meet a higher load standard. the internal steel wire layer must be thicker. This also causes the weight of the tire itself to soar again, coupled with the 100% max torque that erupts the moment the motor is electrified, and the frequent forward and backward pulling from the kinetic recovery system. The tire's rubber molecules are constantly enduring high-frequency fatigue loads. Engineers also had to manually glue a whole ring of expensive sound-absorbing sponges to the inner wall of the tire. The price for all of this is that quotation that makes you gasp in shock. So when you understand the correlation of this chassis trilogy, you will find that if you swap out that ugly factory rim just for the sake of looking cool, you are essentially fighting against 3 laws of physics at the same time. After changing to an aftermarket rim with large holes, your range will immediately plummet by 5% because the wind resistance and turbulence have increased. If the aftermarket rim is too heavy, your acceleration will become sluggish, and the road feeling will become bumpy because the unsprung mass is out of control. If you still want to save money and install a regular fuel car tire, then your sidewall won't be able to support the inertia of 2 tons. Facing the risk of tire blowouts and losing control during extreme cornering. Is maintaining an electric vehicle really cheaper? If you factor in these expensive dedicated tires that wear out in just 20,000 kilometers, and the engineering costs paid in pursuit of every single kilometer of range, you will realize that electric vehicles are actually an extremely precise and expensive physical investment. This is the truth as to why engineers would rather be scolded by netizens for making it ugly and insist on sealing the wheel rims completely. Behind this is a precise gamble concerning 90% kinetic energy recovery, 30% elimination of wheel drag, and a 5% increase in range. Let's take a deeper look at the details of this aerodynamics. When the vehicle speed reaches 100 kilometers per hour, air resistance increases geometrically. Imagine the situation when air molecules hit the wheel rim. A traditional hollow rim is like having countless small spoons constantly stirring the air. This stirred air will form a high-pressure zone inside the wheel arch. This high-pressure zone not only increases backward drag, but also generates upward lift, making the front of your car feel floaty when driving at high speeds, and reducing grip. While the enclosed will cover is like building a smooth wall on the outside of the tire, allowing the airflow to form what is called laminar flow, flowing smoothly along the side of the car body to the rear. This subtle difference might only save a fraction of a kilowatt-hour on short trips. But if you are running long distances on the highway, this could be the lifesaver that lets you stretch it to the next charging station. Many car enthusiasts will ask, then why not just use carbon fiber to make the rim? It's both lightweight and can be enclosed. The answer is simple. That is cost. The price of a single carbon fiber rim could be equivalent to half of a small commuter car. It's fundamentally impractical for mass-produced cars. That's why engineers developed this plastic outer cover solution. Not only is it extremely lightweight, adding absolutely no burden to the unsprung masses, it can also undergo large-scale automated manufacturing on the production end. What's even smarter is that the centrifugal force generated by this outer cover during high-speed rotation is relatively small. Let's talk further about the deep logic of thermal management. Although we say EVs rely on energy recovery 90% of the time, that remaining 10% of mechanical braking still needs to be treated properly. When engineers design fully enclosed wheel covers, they actually still leave some extremely tiny diversion trenches on the edges. The shape of these grooves has gone through fluid dynamics simulations. They normally don't interfere with wind resistance, but when the rim rotates at high speeds, they used Bernoulli's principle to generate a weak negative pressure, sucking the trace amounts of hot air inside the wheel arch outward. This is why even if it's completely sealed, your brakes can still stay within a safe temperature. This is the fascinating part of engineering. It's not black and white, but finding the most perfect balance point amidst endless conflicts. If you really can't accept the look of the factory covers, my advice to you is go look for third-party covers that advertised wind tunnel testing, or at least choose forged rims that emphasize lightweighting. Absolutely do not casually go to a superstore and pick a set of cheap rims that are incredibly heavy and have huge holes. That is wasting every cent of electricity the engineers saved for you. Lastly, we need to reflect on a question. Has the advancement of electric vehicles really saved us money? We saved on expensive engine oil, but got more expensive tire expenditures in return. We saved on the wear and tear of brake pads, but have to endure ugly-looking enclosed wheel rims. This is actually a major transition in the way humans move, shifting from the romance of mechanical structures to the precise calculations of electronics and physics. In the eyes of engineering cores, there is no absolute good or bad, only the inevitability of the laws of physics. Whether to live for coolness or for efficiency, there is no standard answer, but at least before you make a decision, you should see through the underlying logic behind it. After driving an EV for 10 years, when factoring in this hidden cost of the chassis Trilogy, does it really beat a fuel car? This topic is simply too cruel. Specific parts for specific cars is not just a marketing slogan. It is the most basic respect for the limits of physics. If this video has cleared up your chassis misconceptions about ugly rims, please like, subscribe, and share it with more friends who are hesitating about buying a car.